Well, thanks to everyone who came to our seminar. This would be final seminar in this semester. We will have a break till September. But now will have a very nice talk by Professor Adolf Mirotin, and the title is here on the screen. So thank you very much, Professor Mirotin, for agreeing to participate and to deliver a lecture at our seminar. And please go ahead. Thank you.
Thank you. The aim of my talk is twofold. First of all, I want to describe the spectra of generalized Hausdorff operators on the real line in the space L2. And the second part will be devoted to some generalizations to the n-dimensional case. And if I have enough time, I want to discuss also the compactness of Hausdorff operators. The first parts of my talk is based on two following papers. The first paper in functional analysis and applications, and the second one in the Forum Mathematicum. And the last part will be devoted to the problem of compactness and is based on the paper in Russian Journal of Mathematical Physics. Firstly, Hausdorff operators in the following form were introduced by Karapetyants and Rogozinsky. And here, mu is some regular Borel measure on the segment 0, 1. And this is the continuous variable analog of the Hausdorff transformations for sequences and series. In the famous Hardy's book, Divergent Series, one can find the condition of boundedness, the sufficient condition of boundedness of this operator in the space LP on the segment 0, 1, and the theorem that this transformation is regular, is some sense regular, and if this means, this theorem means that this form, this special case of the Hausdorff operator is a sort of an average of the function f. In the first part of the talk, I will consider the following Hausdorff operators. Here, mu is some regular Borel measure on some topological space omega. Kfu is some locally integrable with respect to mu function on omega, the so-called kernel of the Hausdorff operator, and A of u is some dilation family, some measurable functions from omega to r minus 0. If we take the counting measure as mu, we get the special case of so-called discrete Hausdorff operators. These operators takes the following form if mu is a counting measure on the set of z of integers. The most famous example, now I want to list several examples of such operators. And the most famous example is, of course, the so-called continuous Scalar operator. And it continues to be studied to the present day. The second example, the so-called harmonic Scalar operator. Then the Hardy operator with some gamma positive. The Calderon operator, this operator is important for the theory of Hilbert transform. And the Cesare mean of order alpha, and then the Riemann-Liouville operator of fractional integration is closely related to C alpha, to the Cesare mean of order alpha, and the so-called Copson operator. And finally, the Q-calculus version of a Cesare operator, this operator of the following form. Q is some parameter real between 0 and modulus between 0 and 1. And the last example, the seventh example, is the example of a discrete Hausdorff operator. To my knowledge, Halmos, Browns, and Schills, Boyd, Leibowitz, Rodas, Albanese, Bonnet, and Rickert calculated several spectra of some special cases of Hausdorff operator, mainly for discrete and continuous Cesare operator. The modern development of the series of operator begins with the work of Lipton and Morris 20 years ago, more than 20 years ago, where the boundness of some class of Hausdorff operators on the hard space H1 over reals were considered. First of all, the boundedness condition. If the modulus of the family A of u to the power minus 1 over p multiplied by the kernel is integrable with respect to mu, the Hausdorff operator mentioned above is bounded in the space LP for p between 1 and infinity. And the next estimate for the norm holds. This condition is sharp, and this estimate also is sharp, as we will see later. And we shall assume that the condition of lemma 1 holds in the first part of the book. To describe the spectra, first of all, we need to split the space omega in two parts, omega plus and omega minus. Omega plus consists of such u that A of u strictly positive, omega minus of such u that A of u strictly negative, and then we introduce two scalar functions, so-called scalar symbols. Phi of s is the sum of such two integrals over omega plus and omega minus. Of course, we can express phi of s as a single integral, and the so-called adjoint scalar symbol phi star is the difference of these two integrals. And then the following theorem holds. If the condition of boundedness from lemma 1 is fulfilled, then we have for the space L2 over reals that the spectrum of our Hausdorff operator is the closure of the union of ranges of phi and phi star. Next, the point spectrum is the set of such lambda that the Lebesgue measure of this union of pre-images of the single point lambda is positive. And the residual spectrum is empty. So we have the complete description of the spectra of the Hausdorff operator in terms of symbols. And if we have the complete description, of course, we have a lot of interesting corollaries. For example, corollary 1, the norm of this operator is the max of the C primum of such two modulus, modulus phi and modulus phi star. The most convenient, the simplest statement of the theorem we get if the family A of u consists of strictly positive dilations. Then the spectra of our Hausdorff operator is the closure of the range of phi. And the point spectra also is the set of such complex lambda that the Lebesgue measure of the pre-image of the single point lambda is positive. And the norm is the supremum of the modulus of the scalar symbol phi. In the case where A of u positive, scalar symbols phi and phi star coincide. And if the kernel is positive, then the norm equals to this integral. So we see that in this case, the inequality from lemma 1 turns into the equality. So the conditions of lemma 1 are strong and cannot be weakened. the n-dimensional case. The n-dimensional definition we consider in the following form. As above, omega mu is some measure, topological measure space with regular barrel measure mu. K is locally integrable function, and we take the family capital A of U of such non-singular n by n matrices with real entries, such that this family is a measurable family. And the Hausdorff operator with the kernel K we define is the following way. The n-dimensional classical definition, by classical definition, I mean the case where mu is the big measure on the Euclidean n-dimensional space. The classical dimension is due to Lifton and Lerner and to Braun and Moritz 2002. Of course, we begin with the condition of boundedness. If the following condition holds, here we have the modulus of the determinant of the matrix A of U to the power minus 1 over P multiplied by the kernel is integrable, then this operator is bounded NLP for all P, and the next estimate for the norm holds, and we shall assume in the second part of my talk that the condition of lemma 2 holds. To the problem of the describing of the spectrum of the n-dimensional operator, I think this problem is very difficult, and I cannot solve this problem in full generality. But some special case that generalize the one-dimensional case is based on the observation that in one-dimensional case, if we consider the space L2 over reals, all Hausdorff operators are normal. This means, of course, that this operator commutes with the joint operator. And the idea in the one-dimensional case to consider also normal n-dimensional Hausdorff operators. To introduce the main tool, the symbol in this case, firstly, we consider some fixed enumeration on the family of hyperoctants in Rn with J. J runs between 1 and 2 to the power of n, and let the spectrum of the matrix A of U consist of eigenvalues denoted lambda of U J with their multiplicities, and then we introduce the family of scalar functions. Phi ij of S is the following integral, this definition for all P. And we integrate over the such family of U of such U that the matrix A of U maps Vj into Vi. So we have the family of continuous bounded functions on the Euclidean n-dimensional Euclidean space Rn. Here we use the multi-index notation, of course. And then we introduce the matrix function capital Phi with entries Phi ij. This matrix is the member of the algebra. Capital Phi belongs to the matrix algebra of 2 to the power n by 2 to the power n matrices whose entries are bounded continuous functions over the n-dimensional real Euclidean space. And then theorem 2 gives the description of the Hausdorff operator under the following condition. We assume that the family AFU of matrices is a commuting family, and all matrices here are self-adjoint. Then in the space L2 over Rn, we have, firstly, that the spectrum of the Hausdorff operator is equals to the spectrum of the matrix capital phi in this matrix algebra. And this spectrum is the set of such complex lambda. Such sort of lambda that the inf of the modulus of the determinant of the difference lambda minus phi of s equals to 0. This is the set of all points, singular points of the spectrum. And to describe the point spectrum, we introduce for every complex lambda, we introduce the set E of lambda of such S in Rn that the determinant of the difference lambda minus phi of S equals to 0, and then the point spectrum consists of such lambda that the Lebesgue measure of the set E of lambda is positive, and the residual spectra is empty. Of course, if we have the complete description of the spectra, we can find a lot of corollaries. For example, the first corollary about the inverse. The Hausdorff operator under the conditions, of course, of the previous theorem is invertible if and only if this condition holds. The infimum of the modulus of the determinant of the matrix symbol is positive. And the second corollary for the norm. The norm of our Hausdorff operator is the supremum of the operator norms of matrices capital phi of S, and this equal to the maximum of modulus of such lambda that the infimum of the modulus of this determinant equals to 0. And the simplest statements we get if the family of matrices A of U consists of positive definite matrices. In this case, we can use the scalar symbol instead of the matrix symbol. Namely, we introduce the function phi of S of the following form. We call it the scalar symbol. Of course, here we use notations, the multi-index notations. And this is a function on Rn. This is a continuous and bounded function on Rn. And the corollary 3 means states that if the family A of U consists of positive definite matrices, then the spectrum of our Hausdorff operator is the closure of the range of this scalar symbol. And the norm is the supremum of the modulus of this scalar symbol. And the problem is how to generalize these results to the space LP, even for the case of commuting self-adjoint matrices A of U. This is an open problem, and I conjecture that the matrix symbol should be the main tool for solving this problem in the LP case as well, and maybe in other function spaces too. And the last part of my talk deals with the question posed by Liefland in 2007: can the non-zero Hausdorff operator be a compact operator? there is a conjecture that no, that every non-zero Hausdorff operator is not compact. I conjecture even more that every non-zero Hausdorff operator is non-Riesz. Here's a definition due to Ruston of the class of Riesz operators. A bounded operator T on some Banach space X is called a Riesz operator if it is not invertible and its non-zero spectrum consists of eigenvalues of finite multiplicity with no limit points other than zero. So this definition mimics the spectral properties of a compact operator. Of course, the problem posed by Lifton about the compactness is not the spectral story, but the Riesz operator is due the spectral story. There is a lot of interesting characterizations of Riesz operators in the book, for example, of Schechter, in the Schechter principle of functional analysis, in the monograph of Dawson about operators in Banach spaces. And for example, the result of Schechter, T is a Riesz operator in the Banach space X if and only if for each non-zero scalar lambda, T minus lambda E is a Fredholm operator in X. And the last result of my talk is the following. Theorem 3. Let AFU be as above a canonic family of self-adjoint matrices, and let the condition of bound from the lemma 2 holds. Here P is an arbitrary between 1 and infinity, and then the Hausdorff operator, if it is non-zero, is non-Riesz in LP for all P. And it should be noted that several words about the proof. First of all, about the proof, the theorem 2. The main tool for the proof in theorem 2 is some spectral representation of a Hausdorff operator H. It is shown that this Hausdorff operator is unitary equivalent to the operator of multiplication by the matrix function capital Phi in some space of vector-valued functions. And of course, the operator of multiplication by Phi is more simple than the initial Hausdorff operator, and we can, using this spectral representation, to prove theorem 2 and all corollaries of this theorem. It should be noted also that the proof of the theorem 3 about the non-compactness of the Hausdorff operator under conditions of that AFU is a commuting family of self-adjoint matrices uses the matrix symbol in the LP, in LP spaces. This is the fact that suggests that the matrix symbol will be useful in LP, maybe for other spectral problems, for example, for the problem of computing the spectra. As regards the Riesz operators, it should be noted that, of course, every compact operator is Riesz, but also every quasi-nilpotent operator. This is the operator with whose spectra is null, consists only of zero. Every quasi-nilpotent operator is a Riesz operator, and it is known that a sum of a compact and quasi-nilpotent operator is also a Riesz operator. So we have the following corollary of theorem 3. If we have a non-zero Hausdorff operator under the conditions of theorem 3, it is not a sum of a quasi-equivalent and compact operator. It should be noted also that it is known that in Hilbert spaces, the converse is true. Every Riesz operator is the sum of a quasi-nilpotent and a compact operator. And as regards the general case of Banach spaces, to my knowledge, this is an unsolved problem. The conjecture is the statement of the theorem for Hilbert spaces is not true in the Banach case. And it should be noted that the one-dimensional Hausdorff operators considered in the first part of my talk satisfy all the conditions of theorem 3. So we have the corollary 2. Any Hausdorff operator who is non-zero and one-dimensional is non-Riesz is every space LP for P between 1 and infinity. And so it is not a sum of the quasi-nilpotent and compact operator. Thank you for your attention.
Well, thank you very much for a very nice presentation. And we have time for questions. Yes, we
there
have
is a question. There is a question from Nizhny Novgorod. Значит, yes. Have you considered the functions from your Hausdorff operators in correspondence to your previous works?
No, I don't know any work about the functions of Hausdorff operators. It is a new problem, I think.
Is this an open problem? Functions?
In my papers mentioned in the beginning of my talk, I listed 3 papers, and in the first or second of them, the product of 2 Hausdorff operators is considered. So the square of Hausdorff operator is considered as well, and this is only one function that I knew of Hausdorff operator.
Yes, thank you.
Okay, so I saw a question by Professor Ovsyankin, but maybe it was just by mistake. Yes, Oleg, please go ahead.
Can you tell some words about the proof of theorem 2 once more?
Just a minute. Theorem 2. We consider the space L2 our Rn of vector-valued functions from Rn to C to the power 2 to the power n. And in this space of vector functions, we consider the operator of multiplication by capital phi. Capital phi is a matrix-valued function of the order 2 to the power n. And we prove that our Hausdorff operator H is unitary equivalent to the operator of multiplication by the capital phi in this space of matrix-valued functions. And then all spectral problems concern H turn to the spectral problems about this operator of multiplication by phi. This operator
I see.
Is nice, and we can prove
it's nice operator.
These facts about the operator of multiplication by phi, so we get results about the spectra of Hausdorff operator.
You constructed
we can
the
find this proof in my papers. Just a moment. Functional analysis and applications. Here, the case of positive definite of you considered, and in the full generality, the one-dimensional case. And this paper in Forum Mathematicum contains the proof of theorem 2 in full generality.
Thank you very much.
I guess the continuation of this question can be as follows. Can you make some kind of symbol calculus based on your result?
This is a good idea if we can apply functions to the symbol, capital Phi.
Yes.
Of course, then we can apply functions to the Hausdorff operator. Of course. A good idea. Thank you.
Yes. And you can develop a symbol calculus.
Yes. And we can develop the
I may think about, okay. We have a question from Professor Livland.
There was a list. First of all, thank you for this very interesting talk. I'm glad that these questions are considered and solved, maybe partially. There is an open problem. Very good. There was a list of people who worked with spectral properties. Pretty long list with, for example, old results. For example, Billy Rhodes.
Sorry? Just a moment.
Yes. Billy Rhodes.
All results are old. The exception is the work of Albanese, Bonnet, and Rickert.
My question is as follows. There is a mathematician in Seville, Guillermo Corbera. He works for many years with the spectral property of Cesare operators. I know him pretty well. We met many times. He listened to my Hausdorff talks, and I tried to convince him to extend his results. As far as I know, he never tried and never went beyond these promises. But anyway, I believe that in his Cesare papers, one can find something useful, maybe, to be applied to.
Sorry, once more, his name is
Corbera, C-U-R.
C-U-R.
B.
Corbera.
Corbera.
Corbera. B. Corbera. Corbera. Надо будет поискать его работы. Спасибо.
Okay, more questions, please. Oleg, another question?
Yes.
Okay.
Adolf Mirotin, but what about symbolic calculus in LP?
Of course, we have a symbol in LP, but I don't know a result how to use this symbol in LP to study the Hausdorff operator. I have only the result about the unitary equivalence in L2. And something like equivalence in LP will be very, very useful.
Maybe estimates from one side or from another side.
Thank you.
Not equivalence, I guess. Well, it's a question to study, I guess.
Yes.
Okay, more questions, please. Professor Badali, please.
Thank you. My question is following. You investigated the eigenvalues and eigenfunctions of Hausdorff operator, and what application of the investigation of spectrum of Hausdorff operator in the theory of LP space?
I have not any theory in LP space, unfortunately. We have only results in L2. Only. As regards LP, we have only results about the compactness and about the non-Riesness of this operator. Only these results in LP for general P, for all P, and other results only for L2.
Okay. Thank you.
Thank you. Do we have more questions? Well, we had very nice discussion, and I guess no more questions. So let us thank speaker for very nice presentation.
Thank you very much.
Thank you.
Thank you very much. And thanks to everyone who came to our seminar. As I said before, it's our last seminar in this semester. We will have a break till September 1st, and we will come back on September 1st with a new series of seminars. Thanks to all participants, thanks to all speakers, particularly thanks to our speaker, Professor Mirotin, for very nice talk. Well, let's do applause to everyone from seminar, from participants, for speakers. And see you soon in September in our series of seminars. Thank you.